Alrighty, so number 7, 8, 9. Number 7 says, cows flying a helicopter when you drop the bag. When the bag is full in 2 seconds, what is the bag's velocity and how far is the bag fall? So this is sort of the base one. In this one here, the helicopter is hovering, and the object is simply dropped. And how long does it take? 2 seconds, right? And all we want to know is what is the bag's velocity and how far has it fallen? Acceleration is minus 9.8, meaning our change in velocity is 2 times that, or minus 19.6. And since the initial velocity was 0, therefore our final velocity is minus 19.6. And I'm really hoping that you can all do that pretty straightforward, no problem. And I'm actually kind of hoping you can do the rest too, fairly, without too much difficulty, right? V bar equals VI plus VF over 2, 0 plus minus 19.6 over 2, conveniently works out to minus 9.8. And then we're going to multiply by 2 again. Seems like a lot of going forward and backwards, doesn't it? But that's not really the point. It's can you do the question, right? Don't even need a calculator. 3 marks? Easy stuff, Megan? Giveaway marks on the test, right? Like, guaranteed, you got to be able to do it. Okay. Now, what's different in number 8? This time, the helicopter's doing what? It's rising. Okay? So what happens as the object is dropped? Well, it has an initial velocity as well. In fact, the object, or whatever it is, it's going to go up and then down, isn't it, right? Why does it go up and then down? Because it has that initial velocity, right? It's already moving forward. If you throw a tennis ball outside of a moving vehicle, you think it goes backwards, but people on the side of the road are going to see it doing what? Going forward. It's kind of weird when you think about it, actually. Frame of reference, right? Okay, so same steps. Is it still 2 seconds? Yep. So that means that is the same, right? Minus 19.6, that's the same. What's different is that is not the final velocity. Remember, this is only true when what? When the initial is 0, exactly. So we're going to have to do one more step here. We're going to have to go delta V equals VF minus VI. Now, is the negative and negative 9.8 even more important here now than it was before? Like, could we have gotten away with here, if I just ignored that negative 9.8, I still would have got 9.6 here. I would have got 9.8, and it just would have been all positive, right? And basically, it wouldn't have mattered a whole lot. What does this negative really here mean? It just means that the bag, the object, whatever it is, it actually falls, goes down minus 19.6. But in this question here, it's way more important. How come? Do you know why? Positive initial velocity, right? So you've got, when you have that opposite thing, when you have positive and negative, then it's even more crucial. So this is minus 19.6. We are solving for the final velocity, and this is going to be subtract, what is it, 5? Plus 5. Okay, so that's important, because if this wasn't negative, when I take this negative 5, maybe let's just do it like this. Right? When I take that negative 5 over here and it becomes positive 5, if that was positive 19.6, it's going to be a different answer. So it is important. So this now becomes minus 14.6 is equal to the VF, right? It's actually falling a little bit slower than before. How come? Because it started going up. Now, V bar equals VI plus VF over 2. The initial was plus 5. That's important that it's plus. VF is minus 14.6 over 2. 5 plus minus 14.6 is going to be minus 9.6 divided by 2, right? Which is going to be what? 4.5 and 3 minus 4.8 is the average. meters per second, correct. Still 2 seconds. What do you know? What is it? Well, it's minus 9.6. It's not 9.8. How come it doesn't fall as far? Because it went up first. And it only had still 2 seconds. So it goes up and then it comes down. So minus 9.6. But I think the next part says how far below the helicopter is the bag, right? So here's where it was released. What does the helicopter do, Josh? Goes up, right? How far does it go up? This distance here, from there to there, is 9.6. How far does it go up? I have something like VH, maybe, velocity helicopter. I probably have something like that in the solutions. If you looked, V bar equals D over T. 5 is D over 2. Am I right? It goes up 10 meters. There to there is 10 meters. So 10 meters up, 9.6 meters down, but the question says how far below. So I probably wrote something like dt is equal to 10 plus 9.6. How come you don't have to go 10 minus 19 points, or 10 minus 9.6? It's the distance, right? It's not, the direction doesn't matter here, right? The negative, you got to start thinking about that negative sign implying direction sometimes. And I know it's confusing. It just takes experience. You'll get good at it. It's coming. You'll get there. How many marks do you think that would be worth? 1, 2, 3, 4. Yeah, probably 6 marks, right? But hard? Austin, what do you say? Not too bad, right, when you see it? Not too bad. What about number 9? What's the difference in number 9? It's going down, right? Do I need to do this one? I see blank stares from everyone. I should do it? This time the helicopter's going down, which gives that bag, that object, whatever it is, an initial velocity of minus 5, I think it is. What is the bag's velocity? The first step is going to be the same. Okay, you guys said me to do it, and then none of you are watching or paying attention. Nah. Minus 9.18.6, solve for VI. Here the minus VI is, now it's subtract minus 5, right? Be careful. Subtract minus 5 is plus 5, goes to the other side, becomes negative. I get minus 24.6 meters per second. Can't do that yet. Minus 5 plus minus 24.6 all over 2, that's minus 29.6. Half of that is 14.8. So the object falls minus 29.6 meters, but again, how far below the helicopter is the bag? This time the helicopter is going down. Minus 10. So how far below is it? Now maybe we need to draw a picture here, right? Here's the helicopter. The bag falls minus 29.6. The helicopter goes to there. This distance here is minus 10. So what is this? This time it's going to be well, it's 29.6 minus 10. You almost have to take away the directions and actually think it through. And what is the same between this one and the previous one? The distance between them. Is that coincidence, do you think? Nope. It is not. It's just the way it works. Think you'll see a question like that on the test? Especially because I've been harping at it for a while, right? Does this explain, is this pretty much kinematics in a gravitational field, everything you need to know? Yeah, pretty much. Will it be a helicopter and will the guy's name be Kyle? Probably not. Okay, so a little more theory on gravitational fields. And we're going to start talking about weight in moving objects, or weight in moving systems, which is one of the outcomes. We're going to get started today on that. Probably take another day or so next week on that as well. So we're aiming for, like, I said Thursday, I think, right? Test? Yeah. Yeah, probably closer, probably better chance of it being Friday. Friday today. Okay, so let's begin here. You should have this handout. If you came in late, the handout's there at the back where I started to put them, so that you can grab them on your way in. I'm going to try to keep doing that. So here we have a rocket, and it is interacting. Yours doesn't do this because it's on paper, but it's interacting in the Earth's gravitational field. So we know that the Earth pulls on the moon, and some people call this action at a distance. I'd like you to highlight that because it's going to come up in your future life. Action at a distance. If I want to go over there and grab Andrew's water bottle, is that water or what is that? Oh, okay, it's iced tea, yeah. It's like, that's pretty dirty water, man. Okay, so if I want to go over there and I want to knock Andrew's iced tea off, if I want to knock Andrew's iced tea off the table, I actually have to go over there and touch it. I am not a Jedi Master. But interestingly enough, the Earth can pull on this rocket ship without touching it. There is action at a distance. Because the Earth and Moon interact with each other even though they are not in contact. So even though there's no contact, there's still this force. Or we can look at it in a different way. We can regard the Moon as interacting with the gravitational field of the Earth. Force fields do exist. The properties of the space surrounding any mass can be considered to be altered in such a way that another mass introduced to this region will experience the force. This alteration of space is the gravitational field. You've probably seen pictures, you know, kind of space pictures where it looks like a funnel. There's lines to show that funneling, but they don't really exist. Like the lines don't exist, right? It's just sort of a model of how we describe it. It's common to think of distant rockets and space probes as interacting with gravitational fields rather than with the masses of the Earth and other planets or stars that are the source of these fields. The field concept plays an in-between role in our thinking about the forces between masses. So the field concept helps us humans understand how a force can be applied at a distance, how I can knock Andrew's iced tea off without touching it. I do not have a force field. Well, I do, it's a gravitational field. It attracts. It doesn't really push off iced teas or other beverages. All right? Who's seen the Martian there with, what's his name? That game, right? Who's seen the Martian? Okay. So in that movie, the Earth ship, right? The people that they leave him there, they're coming back to Earth, and then they have to go back and get him, right? How do they get up enough speed to go back and get him? They slingshot. They go to the Earth, they get in the gravitational field, and then they get accelerated around, and they go all the way back, right? So they are interacting with that gravitational field. You guys should see that movie. It's a good one. Yeah. Lots of science in there. The book's even better. Gravitational field is an example of a force field. For something in the space experiences a force due to the field. Another force you may be familiar with is a magnetic field. You've probably seen iron filings lined up in patterns around a magnet. The pattern of the filing shows the strength and the direction of the magnetic field at different points in the space around the magnet. Where the filings are closest together, the field is strongest. Where is it strongest on a magnet? Right here around the, what are these called? The poles. where the lines are closest, it is strongest. The pattern of the Earth's gravitational field can be represented by field lines. They are right here. Mine, for some reason, doesn't have them all. I don't know why. Yours has them all, I think, right? Oh, you don't have the pictures? Maybe. Oh, you don't have the magnets. Here's the Earth's gravitational field. These are called field lines. They look a lot like arrows. They look a lot like vectors. They're not vectors. They're called field lines. I wish there was a different way to describe them or draw them that wasn't so much like vectors. Like the iron filings around a magnet, the field lines are closer together where the gravitational field is stronger. At each point on a field line, the direction of the field at the point is along the line. Arrows show the field direction. A particle, astronaut, spaceship, or any mass in the vicinity of the Earth will be accelerated in the direction of the field line at that location. The strength of the Earth's gravitational field, like the strength of its force on object, follows the inverse square law. You guys know what that is? Twice as far, inverse square, half as strong, quarter as strong, right? Same thing with sound, with light. You know how you get really close to a bright light, it's like really bright, what do? You back up, right? It gets less and less intense. That follows that inverse square law. It's strongest near the Earth's surface and weakens with increasing distance from the Earth. So where is it strongest? You guys should probably draw this in here. In close, it's strong. And these field lines actually extend out forever. So out here, the gravitational field is weaker. It's not the length of the line like a vector. It's how close it is to its neighbor. Okay? Just like Red Rover. If you're close to your neighbor, you're strong. It is pretty dangerous, Red Rover. I probably got hurt at least 5 times in elementary school playing that stupid game. I don't know. Yeah, I can't believe they actually let us play that. I'm going to answer a question that you've probably been wondering about since you were a small child. What would happen, Tyler? What would happen if you dug a hole in the middle of the Earth and jumped in? I'm going to explain. The gravitational field of the Earth, I gave you a little break there, Kendra. That was sort of like, my point. Give you a little mental break. Now I'm bringing you back. More science. Gravitational field of the Earth exists inside the Earth as well as outside. To investigate the field beneath the Earth, imagine a hole drilled completely through the Earth, say from the North Pole to the South Pole. Forget about impracticalities such as lava and high temperatures and all that stuff, okay? Just consider the kind of motion you would undergo if you fell into such a hole. You've seen the cartoons, right? Probably. I hope so. There's a Wile E. Coyote or Bugs Bunny. Yosemite Sam, I don't know. The Tasmanian Devil falls in the hole? I can't remember. Maybe. So, if you started at the North Pole, you'd fall and gain speed all the way down to the center. So, you're a little man here. I'll draw him in red so you can see him a little bit better. Okay, so there's the guy. He jumps in the hole. He would accelerate all the way to center, and then he would just hover there, right? Just hang out there at the center for the rest of his life. No? What would he do? He would, in fact, start falling up and slowing down. Yeah? If you start at the North Pole and you'd fall and gain speed all the way down to the center, then overshoot and lose speed all the way up to the South Pole. You'd gain speed moving towards center and lose speed moving away from center. Without air drag, the one-way trip would take nearly 45 minutes. 45 minutes to fall all the way through the Earth. Speeding up as you go towards center, right? And then slowing down. And what would happen, assuming that the Earth was perfectly round, how far would you get? If I jumped in the hole right here, 45 minutes later, I come out in a classroom in Australia. Which orientation would I be? Yeah, I would. If there was a hole right here in Australia, I'd pop up, feet first, upside down, exactly like this high, right? Right, like completely upside down, and then what would happen? I'd fall right back down again. And then I'd pop out of this hole. Another 45 minutes later, I'd go.
Then we get to the.
And yeah. Grab me, because otherwise I'd go back down again, right? If you fail to grab the edge, you'd fall back towards center, overshoot, and return to the North Pole at the same time. Now, if you repeat this with some kind of accelerometer, okay, that measures acceleration. Now, would you accelerate at a constant minus 9.8? And the answer is no. You know why? Why is the acceleration at the center E0? Do you stop? No, I was lying when I said that. Why? You wouldn't stop, right? You wouldn't stop. You would just stop accelerating. You'd stop speeding up, and then you'd start slowing down, right? But why is the acceleration 0 there? Like, if you could climb a ladder all the way down, you could actually jump off the ladder and just hover there. Exactly. All of that gravitational force. Gravity is because of mass. Where's all the mass? Around you. You are in the middle. There's no mass to be attracted to. You are, in fact, attracted this way and this way and this way and this way and this way. Kind of weird. So repeat this trip with accelerometer of some kind. Your acceleration at the beginning of the fall is g minus 9.8. You'd find it progressively less as you continue toward the center of the Earth. Why? Because as you're being pulled downward toward the Earth's center, you are also being pulled upward by the part of the Earth that is, air quotes, above you. Right? Like right here, you've got all of this mass below you pulling you down. Don't let it get you down. But you're also being pulled up by this mass. And again, this is based on the Earth being a complete sphere, right? In fact, when you get to the center of the Earth, the pull down is balanced by the pull up. You are pulled in every direction equally, so the net force on you is 0. There is no acceleration as you whiz with maximum speed past the center of the Earth. The gravitational field of the Earth at its center is 0. Sounds like something from a James Bond movie. Interestingly enough, you would gain acceleration through the first few kilometers beneath the Earth's surface because the density of surface material is much less than the condensed center, blah, blah, blah. The mass of the Earth above you exerts a small backward pull compared to the disproportionately greater pull of the denser core material, blah, 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 right? It's based on, this idea is based on constant density of the Earth, right? But it is actually different densities. Now, you're probably wondering, oh, if you've got a clicker, go ahead and answer this. If you don't, just answer it on the side of your paper. If you stepped into a hole through the center of the Earth and made no attempt to grab the edges at either end, okay, you didn't try to stop, what kind of motion would you experience? Okay, you guys, back to me now, okay? I know, concentration for more than 30 seconds, really challenging, I get that. You'd fall all the way through at a constant speed and stop when you reach the other side? You'd fall all the way speeding up the entire time and stop when you reach the other side. How can you speed up the entire time and stop when you get there? Can't. You would oscillate back and forth with a changing speed. This is called simple harmonic motion. Or you would oscillate back and forth with a constant motion, simple kinematics motion. Which one do you think it is? A, B, C, or D? Did I press start? No. Oh, I didn't even start the class, for crying out loud. And I signed everyone up, didn't I? Okay, why won't it let me start it? Okay, this is not worth it. Why won't it let me do this? It won't let me do it. Never mind. Which one is it? C. The answer is C. You would oscillate back and forth with a changing speed. You would oscillate back and forth in what is called simple harmonic motion. Each round trip would take nearly 90 minutes, so 45 minutes there, 45 minutes back. Interestingly enough, we'll see in the next chapter, actually it's grade 12, that an Earth satellite in close orbit about the Earth also takes the same 90 minutes to make a complete round trip. So if you fall all the way through and back, 90 minutes. If you went all the way around and came back like that, also 90 minutes. This is no coincidence, for if you study physics further, you'll learn about an interesting relationship between the simple harmonic motion and circular motion at a constant speed. You probably won't. I wonder where this goes. Halfway to the center of the Earth, would you weigh more or would you weigh less than you weigh at the surface?
Less.
Halfway to the center. Halfway to the center. Hannah, put the phone down, please. Halfway to the center. Way more? Like, you mean like W-A-Y more, or? The correct answer is half weight. You would weigh less. Why? Because you've got right there, you have all this mass above pulling you up. Actually, I went through those the wrong way, right? Pulling you up. You've got mass above pulling you up, so you would weigh less. Pretty sure. Let me check the fine print. You would weigh less because the part of the Earth's mass that pulls you down is counteracted by the mass that pulls you up. Okay. We talked a little bit about this already. Wait, okay, I'm losing you guys. Come on, just try and focus. I don't know how you guys are going to handle a post-secondary lecture. I really don't. Because I am way more entertaining than Professor Quackenbush, let me tell you. Yeah. Real professor. We're going to talk about weight and weightlessness. The force of gravity, like any force, causes acceleration. Objects under the influence of gravity accelerate toward each other. We're almost always in contact with the Earth. For this reason, we think of gravity primarily as something that presses us against the Earth rather than something that accelerates us. The pressing against the Earth is a sensation that we interpret as weight. And the more mass you have, the more weight you feel. Stand on a bathroom scale that is supported on a stationary floor. The gravitational force between you and the Earth pulls you against the supporting floor and scale. By Newton's third law, the floor and scale in turn push upward on you. So I jump on the scale, gravity pulls me down, I push on the scale pushes up on me. What's that force called? That upward force. Normal force. And then it registers, and it tells me I'm holding. I did. It says 0. Now it's like, oh yeah, there it goes. It just sucked. 850 newtons. Needs a little bit of lubrication, I guess. Located in between you and the supporting floors are springs inside the bathroom scale. The springs are compressed by this pair of forces. The weight reading on the scale is linked to the amount of compression of the springs. If you repeat this weighing procedure in a moving elevator, like we have right here at school, who's been inside the elevator here? Nobody? No one in this room has been inside that elevator. Yeah? Is it really fast, Shelby? It's like you probably fell asleep in it there, right? It's incredibly slow. If you repeat this weighing procedure in a moving elevator, you would find your weight reading would vary. Not during steady motion, but during accelerated motion. Only when you are accelerating. What's the net force right now? 0. When I'm accelerating, what's the net force? Some number, right? Which means my acceleration is less. Am I accelerating at 9.8? No, but if I'm accelerating at a greater speed, right, at some speed greater than 0, there's going to be a net force, which causes me to weigh more. If the elevator accelerates upward, the bathroom scale on the floor push harder against your feet, and the springs inside the scale are compressed even more, and the scale shows an increase in your weight. Do you have these pictures? Yeah. So when you are accelerating upward, and you maybe should put accelerating here, accelerating upward, when you're at the bottom, when you're on the ground floor, you guys have had this feeling, right? If you're in an elevator that's in a really tall building, maybe CN Tower or something like that, at the start, how do you feel? Your knees buckle, you feel really heavy. How come? You're accelerating. You feel heavy. You literally feel heavy. Then you reach a constant speed and you feel fine, right? If the elevator accelerates downward, the scale shows a decrease in your weight. At the top, right? When you're at the top of that CN tower, and it falls away from you, how do you feel? You feel kind of light. Your stomach comes up into your mouth, you kind of, right? You don't feel very good. You weigh less. Gosh, what is so important? You are accelerating downward. And if you are unlucky enough that the cable breaks, then you are in free fall and you have no weight at all. If the elevator cable breaks and the elevator falls freely, the scale reading would register 0. According to the scale, you are weightless. Would you really be weightless? You certainly wouldn't be massless. The answer to this question depends upon your definition of weight. Most people think it's like how heavy you feel, right? You still have a force on you. You just can't measure it. If you define weight as a gravitational force acting on an object, then you still have weight whether or not you are freely falling. Astronauts in Earth orbit who float freely inside their capsules are still being pulled by gravity and therefore have weight. But if you're in a falling elevator and the astronauts in the falling satellites don't, but you in the falling elevator and the astronauts in the falling satellites don't feel the usual effects of weight. You feel weightless. That is, your insides are no longer supported by your legs and pelvic region. Your organs respond as though gravity were absent. You are in a state of what's called apparent weightlessness. It appears that you are weightless. You are not. You just feel weightless. To be truly weightless, you would have to be far out in space, away from the Earth and other attracting stars and planets where gravitational forces are negligible. Truly, like light years away. In this truly weightless condition, you would drift in a straight line path rather than in the curved path of an orbit, which you probably wouldn't even notice. You would be dead, but you know. In a more practical sense, we define the weight of an object as the force it exerts against the supporting floor or weighing scales. According to this definition, you are as heavy as you feel. So if you want to lose some weight, just think about it. I'm weighing less today. The condition of weightlessness is then not the absence of gravity, but the absence of a support force. That queasy feeling you get when you're in a car that seems to leave the road momentarily when it goes over a hump, or worse off, a cliff, it's not the absence of gravity. Gravity doesn't disappear. Gravity exists in space. It is the absence of a support force. Astronauts in orbit are without a support force and are in a sustained state of weightlessness. This causes space sickness, so they get used to it. And I'm going to finish you off with a movie.